This next section, still in the chapter on electrical current and resistance, is module 25.4, and it relates to power, or if you wish, energy loss. Well, as you know, energy is lost when electricity flows through things, and that comes from a heating effect, always heat. So as the electrons race through something, here's an object, again connected to a battery, and as a potential difference exists across these, the electrons are going to try to go from the negative to the positive. As they go this way, and remember that means that the current flows in the opposite direction. So I goes this way when the electrons go in this direction. So the electrons are going to flow back here, but they have to fight to get through the material, some materials more than others. If they're metals, they have outer electrons that are not strongly attached, which means that if you have something that's something like silver, it only has a few outermost electrons, and they're very easily knocked off of the ion, and so they can jump from atom to atom. Well, the energy loss is just a formula that you have to learn. The power that's lost, or the rate of losing energy, is given by a formula. Power is equal to current times voltage. It's a little bit more complex when we're dealing with alternating current. Now you also remember that V is equal to I times R, so sometimes you will see this written as I squared times R. This is the one you really have to remember, so I'm going to put a bigger box around here. And if you think about long-distance power lines, we really want to keep high voltages and low currents, because you can see here that low currents this actually depends upon the square of the current, and therefore you want really low currents and high voltage. If we think about how this would apply, if we take something like a car battery, which has 12 volts, and we had a current flowing in there of 2 amps, then we can see that we would have a power loss of 24, and what would that be? 24 watts. So that's the rate at which power would be lost if a car battery is connected to something and it allows the flowing of 2 amps of current through it. Well, 24 watts is going to get pretty warm pretty soon unless you have a method of power dissipation in the substance. And so that's very important. I might mention in ordinary households, you would say, what are the trade-offs between using high voltage or high current? You could say, well, for a given power, one thing I could do is I could have very, very high voltage and very, very small currents. Why would I want small currents? Well, you want small currents because if I have, I don't want losses in there. The high voltage, if I use a higher and higher and higher voltage, it means that I don't have as much current flowing, so I could use a smaller wire. So I could use a little tiny wire if I have a high voltage, because I have very little current that's flowing in there. And so therefore, I'm not going to get as much heating effect. But there's a problem with high voltage. In your household, if you had 1,000 volts in your socket between one side and the other side, you would have arcing and all kinds of problems. This would be terribly dangerous to have that much voltage. You would have to keep your wires for the left and the right side, not in the same container, or like when you normally see a wire, it's wrapped like this for the household wiring, because you would get an arc between these at 1,000 volts that'd burn your house down from the arcing. So electrocution is a problem with high voltage. You say, well, let's lower the voltage down to where it wouldn't even hurt us practically. Well, you can do that. For example, with a car battery, you only have 12 volts. You can grab the battery for a car, and that 12 volts will not hurt you at all. So you can say, try low voltage. If we have real low voltage, that's fine, but you have to watch out, because then the wire has to be very thick that's going to carry that current. And so this is a cost and an expense of keeping very large wires in your home, even though you have low voltage. These very large wires, if they were bent and bent and bent, can develop a crack in one side, and then they become very thin at one point. And if that happens, then in fact this can heat up a lot and it can burn your house down. So whereas electrocution is a problem with high voltage, fire is a problem with very, very high currents. Many of you have felt a wire that's been attached to a battery when you try to jump start another car. And if those are cheap cables that are not very thick, that can get incredibly hot and burn you. So you know the danger that's involved there.